Hello everyone. So let us continue with the next type of problems. So we have already dealt with cantilever problems with different type of loadings. The next type of problem is simply support beam. So again, this is again solved by moment area method. So this is a simply support beam in which one end is hinged, the other end has a roller, and there is a point load at the center C, point C, and which is placed exactly at half of the distance, that is L by 2 and L by 2. So the question is determine the slope and deflection at the mid span. That means you're supposed to find deflection at C. So once you draw this, the next thing is you have to draw the deflected shape of the beam. So again, in this deflected shape of the beam, wherever there is a load, the deflection is maximum. You can see here, you can just, when you apply the load, the beam deflects. So this is the original position of the beam, and this is the deflected position of the beam. So at the supports, you can just see here, at the supports, deflection is 0. At the center, it is maximum. Again, at the support, it is 0. You can see here at C, deflection is maximum. I've written a delta C as maximum. Next, at A, just draw a tangent like this, straight. Draw a tangent with respect to the point and the deflected curve. So whatever this rotation is happening, that is theta A. Similarly, at B, draw a tangent. And this tangent will give you the deflection, that is rotation at B. So you can notice here, we have shown rotation at A, rotation at B, which are maximum. Similarly, deflection at C is maximum. So we're going to find all the maximum quantities here. That is theta A, theta B, and delta C. Okay. Now, determine the slope and deflection at the midspan. So first, as usual, draw the deflected shape of the beam. Next, the bending moment diagram, followed by M over EI diagram. We know that, now this is the bending moment diagram. So we know that bending moment at the support is 0. And at the center below the load is maximum. So it's a point load. So we've written here as WL over 4. So WL by 4 is the maximum bending moment at C. If you divide this WL by 4 over EI, then we get M over EI diagram. So this is the M over EI diagram. So this is the diagram which we'll be using. Next. So first thing is we'll find rotation at A and as well as B. So to find out rotations, that is theta A, and theta B, we'll be using Morse first theorem, or which is called as Morse slope theorem. So now you can see here theta C. Now this is theta C, delta C. If I draw a tangent here, if I draw a line like this, so that will give me a theta C. But theta C, when I draw this line here, theta C is 0 because there is no rotation happening here, because this deflected shape of the beam coincides with the line here, that is the tangent. That's why theta C is 0. So now this becomes our reference point. So theta C is 0. Now this is the reference point which will be measuring with respect to theta A. Likewise, this theta C at this point, theta C, reference point, minus theta B will give us theta A and theta B respectively. So now, first, theta A minus theta C. So theta C is here, which is 0. Okay. So theta A minus theta C is equal to, so we'll be taking only left half the portion. So if you want to find theta A, so this is only this part will be taking care. That is between A and C, because theta C is the reference point and theta A is the rotation which you're supposed to find out. So only we'll consider this point. Okay, and as it is, see, this is symmetrical about this axis. So it's symmetry. So if you find theta A, it's as good as finding theta B. But of course, only the sign changes. So See here, I'll be treating only AC. I'll be considering only AC portion, and then theta A minus theta C. So theta A minus theta C is equal to area of M over EI diagram, only this portion, M over EI diagram between A and C. So area of this M over EI diagram is given by, so only treat this. So area of a triangle. So this is the triangle area, half into base. So base is L by 2. Height is WL over 4EI. WL over 4EI. So this is half into base into height. So that's why. So it is WL square over 16EI. So the answer is positive. So answer is positive means rotation is clockwise. Similarly, now if you want to find theta B, it would be just the opposite of theta A. Now see here, theta A is WL square over 16EI clockwise. So theta B would be minus WL square over 16EI. So theta B is, this is plus clockwise, minus, this would be minus anti-clockwise. That's why theta B is WL square over 16EI, anti-clockwise. Now, theta max would be obviously at A or B, that is WL square over 16EI at the supports. Now to find the deflection, so deflection, maximum deflection is at the center. So maximum deflection is at the center. So theta C is nothing but it is moment of M over EI diagram. That is moment of area of M over EI diagram between A and C, about A, between A and C. So we are going to consider only this portion because theta B would be just the opposite. So only between this. So we are taking an M over EI diagram also only about AC. So now see here, always will find moment about the support at this portion, about the support. In the previous problem also, if you have noticed, we used to find moment at the free end. That is, if you want to find this moment, it would be a free end, or wherever we are supposed to find the deflection. In cantilevers, we'll find out that would be delta C would be with respect to the point C. But here, we're finding moment at the support. You can see here. So finding moment at the support. So it is a moment of area of M over AI diagram about A. This is in case of moment area method. So we'll find moment with respect to simply support. We'll find with respect to the support itself. So this would be moment of M over EI diagram. That is nothing but, again, same thing, area of M over EI diagram into CG distance with respect to point A. So area. So we have already found out area here. So it is WL square of 16 EI. That's what I've written here. WL square of 16 EI into its CG distance. CG with respect to A. Again, area of, this is the triangle. CG of the triangle measured from the apex. So measured from the apex is 2/3. So 2/3 of L by 2. Only AC distance. So 2/3 of L by 2. So when you solve this, when you simplify, it is WL cube by 48 EI. So this is delta max or delta C. So you can see here, we have found out all the maximum quantities. That is maximum slope at A, maximum slope at B, and maximum deflection at C. Okay, and you consider the next problem. Okay, now check this out. Again, same thing. Here they asked, determine slope and deflection at the midspan of the loaded beam. Okay, by moment area method. So again, it is a simply support beam with the UDL, and exactly at the center there is C, which is half of the distance. It is L by 2 and L by 2. This is the UDL W per unit length. Okay, so now again it is symmetrical here. After you draw this diagram, next you have to draw the deflected shape of the beam. So as usual, at the support the deflection is 0. It rotates like this, and maximum deflection is at C, that is delta C, and again it joins to this point B. Okay, after this at A, draw a tangent which passes and touches this deflected shape of the curve, and this would be theta A. Similarly, draw a tangent here like this, so that it would be theta B, and delta is nothing but the vertical deflection. So delta C is the vertical deflection, which is maximum. So all these are maximum quantities which you are finding. Theta A, theta B are maximum at the support, and delta C is maximum at the center. All right, so first we'll find slope as well as, that is theta A, and then followed by deflection C. Okay, now see here, first theta A. So theta A, again, it falls only in this quantity, that is AC, only in this span, which is at a distance L by 2. So we'll be drawing the M over EI diagram. So it is a simply support beam with the UDL. So it is parabolic like this. So that is WL square over 8 EI. So it is like this, WL square by 8 is actually the bending moment of a UDL with a simply support beam. And because it is M over EI diagram, we'll be dividing it over EI. So now it is WL square over 8 EI. And you can notice that W is a small w here, which is nothing but the UDL. That's why it's small w L square over 8 EI. All right. So let's start with this. So this is theta A. If you want to find theta A, apply Morse's first theorem, that is slope theorem. So it is nothing but, it is the area of M over EI diagram between A and C. So this is the area. Because it is symmetrical, so whatever is theta A, obviously would be same thing, would be theta B with a different sign. So between A and C, so theta A. So you have to find theta A here. So area of M over EI diagram, this is the area, M over EI diagram between A and C. Okay, so as usual, let's start this. So area of this parabola. Okay, so area of this parabola is 2/3, because it is curved like this. So it is 2/3 of X and Y. So 2/3, X is L by 2, Y is WL square over 8 EI. So when you solve this, so you get theta A, WL cube by 24 EI. And the answer is positive. So that means it is a clockwise rotation. So if you want to find theta B, it would be minus theta A. So theta B is minus, same magnitude, but with a different sign, with a negative sign. So it is WL cube by 24 EI, but the sign is anti-clockwise, so rotation is like this. Next, maximum deflection. So if you want to find maximum deflection, it is maximum deflection, again, that is the delta C. Apply Morse's second theorem, that is deflection theorem, and it says that if you want to find delta C, it is the moment of area of M over EI diagram between A and C about A. Again, here, because it's a simply support beam, we're finding moment with respect to the support. So that's why we are taking moment about A. So, and is again in simple terms. So if you want to find delta C, it is area between A and C, area of M over EI diagram between A and C, into CG distance about A. So now, area we have already found out, that is WL cube by 24 EI. So WL cube by 24 EI into CG distance. Okay, so CG distance here is 5 by 8. Again, all this things is already shared in the PDF, wherein, okay, this is already shared in the PDF. If you want, I'll show it once again. So area of a parabola or a sector is 2/3 of X and Y. Okay, you can notice, you can check this out here in this table. So there is a semicircle, there is a parabolic or sector circle, there is a cubic parabola, and there is trapezium. So you can see here, this area. Now this is the parabola. So area is 2/3 of X and Y. And if you want to find the CG from the right end, that means from this curved end, if you want to find the CG, it is 5 by 8. 5 by 8 times X. Okay, so that's how we are taking the centroid as 5 by 8 times of X. Okay, the same thing is used here. So this is the area which we've already found out. and the CG here is 5 by 8 times x, that is only this distance, L by 2. When you solve this, you'll get delta C, that is 5 by 384 WL cube by WL raised to 4 over EI. This is at the center. So maximum deflection at the center, maximum rotation at the support. Okay. So the next type of problem here is same, simply support beam, but this time there is difference in the I values. You can check this out. There is a difference in the I value. So it is divided here. It is a simply support beam with a point load at the center C, but the span is distributed into 3 parts. You can see it's a total 9 meter. It's divided into 3, 3, and 3. So the first 3 meter has I, only I value. Second, third meter has 2I, and the third meter has only I again. Okay. Again, for this type of problem, again, we know that bending moment is maximum at the center. So first thing is draw the bending moment diagram as it is. Forget about all the I's. Just draw the bending moment diagram. So it is W L by 4. Bending moment at the center is WL by 4. Okay. Now, we'll be splitting this into 3 parts here. If you want, there's another method. If you cannot remember the formula, like for simply support beam with the point loaded at the center, if you don't know the formula or cannot remember the formula, so the easy method is, see here, it's a point load, okay, and it is symmetrical. It is exactly at 4.5 meter. If you check this out, it is exactly the center, 4.5 meter. Okay, so now this load gets distributed equally on the supports. So 20 kilonewton downward. So which gets equally distributed on both the side of the load. Because it is placed in the center, this 20 kilonewton downward load should be balanced by the supports. So 20 gets distributed here. So downward load is 20. So upward load has to be 10, 10 each. Now, then the system is said to be in equilibrium. Now see here, this is 20 kilonewton acting downward. So upward force is equally distributed. So it is 10 above, this is also 10 above. Okay, so now it is balanced. So reaction at A is 10, B also it is 10. So if you want to find bending moment at A, so bending moment at A and B is 0 because these are the supports. So it supports, the bending moment is 0. So that's why we've written 0. Next, bending moment at C. So bending moment at C, there's a point load here and it is exactly placed at center. So it has a maximum bending moment. So how much is the maximum bending moment? That is what we're going to find now. So bending moment at C. So to the left side of C, just check out how many loads. So this is point C. To the left side, there is only one load, that is RA, and it is going anti-clockwise. Sorry, this is going clockwise here. To the left side of C, there is only one load, 10 kilonewton, and this is going clockwise. So to the left side, clockwise is positive. So it is 10 into its perpendicular distance. So perpendicular distance at C is 4.5 meter. So it is 10 into 4.5, which is 45 kilonewton meter. But there is another point which we are finding, that is how much is the bending moment at 3 meter from left support. We have to also find the bending moment at a distance 3 meter. Now why we are finding this is because at 3 meter there is I value is only 1, and after 3 meter it is 2I. That's why we are doing this additional step, that is finding the bending moment at 3 meter from the left support. So bending moment 3 meter from the left support, that is at A, is same thing. If you check this out, how much is the bending moment? So 10 into 3 meter. So 10 into 3. So 10 into 3 is 30 kilonewton meter. So after you find out this, so we'll draw the bending moment diagram. So at C it is maximum, that is 45, and at 3 meter here it is 30, and of course at this portion also it will be 30 only because it is symmetrical. Now, next point is you have to divide this bending moment diagram with respect to EI values, because our main matter of interest is the M over EI diagrams. Now, see here, how to draw this. Check this out carefully. Now, at A and B, bending moment is 0. Okay. So, next, bending moment at 3 meter. Okay, bending moment at 3 meter. So, at 3 meter at this point, you can see here, there are two ordinates. Now, actually, this is 30 meter. Bending moment, 3 meter is 30. So I have shown here 30 over EI, because I value is only I here. So I have shown it here 30 over EI. So this is to the left side. To the left side of 3 meter of from A, it is 30. Now, the same thing, if I draw this if I see this to the right side, but to the right side, see here, to the right side of this point, it is 2i. So what I do here is, to the right side, I'll show it as 30 divided by 2ei. So 30 divided by 2 is 15. So this 15 over ei is to the right side. See here, at exactly 3 meter, there are two quantities. So to the left side of this 3 meter, it is 30 over EI. To the right side of this 3 meter, it is 15 over EI. And that is because of the EI values. There's a difference in the EI value. One is I, the other is 2I. So that's how I've written here 15 over EI. See, understanding this step is very, very important, because these are like the deciders. If you understand this thing, then rest all is just simplification. You have to apply the theorem and solve. Okay, I'll repeat this once again. That is, to the left side of this point, it is I. To the right side of this 3 meter, it is 2I. So accordingly, see here, bending moment diagram actually is 30 over EI. It is 30 at this portion, 3 meter. So the left side, I'm going to divide this by 30 over EI. Similarly, to the right side, the same 30, I'll divide it by 2, because it should be divided by 2 EI value. So 30 divided by 2 is 15 over EI. Now here, all these values will be measuring from the base. So actually, if you want to see this 30, it is measured like this from the base. So from the base, it is 30, and from the base, it is 15. This is how you measure this. Of course, when you're drawing here, we show it only the points here, but all these values are measured from the base. Okay, so it's 30 and 15. So this part is over. Next, similarly, now this is 45 at C. Maximum bending moment is 45. So 45, but again, it is in the span of next third meter. So you have to divide this 45 divided by 2. So 45 divided by 2 is 22.5 over EI. So that's how I've shown it here. 22.5 over EI. And see here. Next, how to draw this up to this point. So what you'll do is, first mark the points here. And all these points should be relatively with respect to the magnitude. There should be some difference. You see here, 30 should be maximum. Then 15 should be again lesser than that. And 22.5 should be obviously in intermediate value. So it's an intermediate value. It should be slightly in between this. So after this, just mark all these points. And similarly, this would be just the replica, because it is exactly at the center, symmetrical load. So when you flip it over, it should be same. So obviously this at the next third meter is 15 over EI, 30 over EI. This is just the same. Now, again, because it is symmetrical, apply the slopes first. You have to find, we'll use the theta A. Okay, theta A, theta B. Again, if you find theta A, it is as good as finding theta B. And then maximum deflection at C. So always rotation in simply support. Remember, in simply support beam, rotations are maximum. That is, the theta values are maximum at the support, and deflection is maximum at the center. That's how we are going to find this. Now, again, because it is symmetrical, we'll take only this AC portion here. So we'll apply first moment area theorem, that is slope theorem, only between AC. So between AC, first theta A minus theta C. At the center, we know that theta C is always 0. So theta A minus theta C is equal to area of M over EI diagram between A and C, only this portion. Okay, so again, area. Now if you check this out, we have split it into 3 parts. Okay, 3 parts. That is, we can take this as, this is one triangle, this is another triangle, and this is a rectangle, small portion. Now see here, first half this triangle, bigger triangle, only this triangle. So it is half into base. So base is 3 meter at this portion, 3 meter. Next height. See here, actually this 15 is to the right side. To the left side is 30. So it is half into base 3 meter. Height is 30. So it is 30 over EI. So one portion is over, bigger triangle. Next, we'll take this smaller triangle. Okay. Now this small triangle. Okay. So in this small triangle, this is, here, total is 22.5. Okay. And this portion is 15. So if you want to find this height, only this portion in the triangle. So it is 22.5 minus 15. Okay. So again, so this triangle is half into base. Base is just 1.5. You can see here, base is 1.5 meter and height is 22.5 minus 15. 22.5 minus 15 will give me only this portion. Okay, next, plus, this is a rectangle now. So rectangle is length 1.5 into breadth. So length into breadth is, so this is 15 into 1.5. Okay, so 15 over EI into 1.5. So when you solve this, again see here, solve this quantities individually, because these are the areas which will be considering to solve the next deflection. So this is the area of the first bigger triangle, area of the smaller triangle, next area of the rectangle. So this is theta A. So theta A is measured in radians. So theta B is just the negative side, that is theta B is just minus theta A, which is minus 73.125, that will be in radians. So we have found out the maximum slopes, that is theta A and theta B. Next we are finding the deflection. So deflection we are finding at C. So wherever there is a load at the center, there is a maximum deflection. That is what we are going to find now. Okay, so again with the theorem, so deflection is maximum at the center. So apply Morse second theorem to find out the deflection. That is nothing but area into CG distance. So moment of M over EI diagram between A and C about A. Again, I've told you we have to find moment only with respect to the given support. So it's nothing but area into CG distance, area into CG with respect to A, area into CG. That's all. First, area. Now this is, again we have already solved this. So take up this value. So we know that first is a triangle, bigger triangle. So area of a bigger triangle, then it's CG, area of a bigger triangle, then it's CG. Now you see here, with respect to A, the CG of a triangle measured from the apex is 2/3 of the base. Base is 3 meters, so 2/3 of 3. So area into CG. Next, area of this triangle, small triangle. So we have already found area. So I've written area into CG distance with respect to A. So again, you are measuring like this. See, when you measure with respect to A, it's like this with this distance. So centroid is somewhere here. So with respect to apex, it is 2/3 of 1.5, 2/3 of 1.5, but you are measuring with respect to A. So this is 2/3 of 1.5. You are measuring with respect to A, so you have to add plus 3 for this. So 3 plus 2/3 of 1.5 will give us this quantity. Next, plus the third quantity, that is rectangle, area of a rectangle, 22.5, write it here. Then now this is the rectangle. So centroid of a rectangle is 1.5. So this distance is 1.5 divided by 2. But you're measuring with respect to A. So that's why 1.5 divided by 2 plus 3 meter. Okay. So area into CG, area into CG, area into CG with respect to A. Solve these values and then you'll get delta C. Again, the answer is positive, so the reflection is downward. So the main moment area method is, you should know the main important thing is you should know how to draw M over EI diagram or the bending moment diagram. So once you're thorough in that, next is you should only apply the theorem. So the first theorem gives you area of M over EI diagram. Second theorem, that is area into CG distance, will give you the deflection. Okay, now check this out. Next type, determine the slope at the support and deflection at the mid span. Now AB is a simply supported beam, and in both the cases there are two types of loadings here. One is a UDL and the other is a point load. UDL and a point load. So what we'll do here is, because there are two types of loading, we'll split this into two different bending moment diagrams. Okay, I will split this into two different. So there's a UDL throughout. Again, it is symmetrical, and there is a point load at the center, which is also symmetrical. So we'll split this. So first, due to UDL. So we know that simply supported beam with the UDL, the bending moment diagram or the bending moment is maximum at the center, and that is WL square over 8. So W is 5, L is 5 square divided by 8. So WL square by 8 EI is nothing but 15.625 over EI. So we have written this like this. Next, this is due to UDL. Next, due to the point load, that is 50 kilonewton. So it is WL by 4. Simply support with the point load at the center is WL by 4, that is 62.5 over EI. So W is 50 into 5 divided by 4 is this parameter. Now this is one approach. The second method, if you cannot remember the formula for parabola and that is UDL as well as point load, you always have the traditional method, that is find the reactions. Again, use this equilibrium conditions, find the reactions, and once you find the reactions with respect to any given point, you can find the moment. Okay, these are the two M over EI diagrams. Now considering this, we'll find out theta A. Okay, theta A, they have asked you to find rotation at the support and deflection at the midspan. So first thing is theta A. So you can check this out. Theta A is area of M over EI diagram. See here, there are two different diagrams. So you have to consider both of these. You have to consider both the areas of the UDL as well as the point load. So area of M over EI diagram between A and C. M over EI diagram between A and C. A and C. Okay. So first, area of this portion. So area of a sector or a parabolic curve is given by 2/3 of base, that is 2/3 of x and y. So it is like 2/3. X is half of 5 meter, that is half of 5 meter, that is 2.5. This distance between A and C is 2.5. So 2/3, 2.5 into this height, that is 15.625 is this area of a UDL. Next, area of this triangle, half into base is 2.5, height is 62.5. So when you solve this, so again solve this individually, because these are the quantities which we'll be using further. Solve this individually over EI, this individual over EI. So theta A is 104. Again, answer is positive. Theta B would be just the opposite with a negative sign. So that is minus 104.165 over EI. Next, maximum deflection is at C. So maximum deflection, again same thing. It is moment of M over EI diagram moment of M over EI diagram between A and C about point A. So again we are taking moment between A and C for both the figures about point A. So area of this into its CG distance, area of this figure into CG distance. Okay, so now check this. So this would be first area. We have already found out the area. So first figure, parabola area is this. So area of this. Next, CG distance with respect to A. So with respect to this end, if you want to find the CG, it is 5 by 8 times 2.5 meter. So how for this? 5 by 8 times 2.5 meter. Next, plus. Next quantity. So this is the area of a triangle. So area of a triangle. Again, triangle with respect to A is 2/3 of 2.5 meter. 2/3 of 2.5 meter. So when you solve this, you'll get delta C. So delta C is now 170.88. Again, answer is positive. That means deflection is downward. Okay, so the next problem is, again, determine maximum slope and maximum deflection for the following beam. So again, we know that the simple support beam, maximum slope is at the support and maximum deflection is at the center. Okay, now see, it's a simple support beam and there is a moment at end A clockwise and at end B anti-clockwise. So these are the moments like this, only at the ends. So after this, draw the deflected shape of the beam. Now see here, deflected shape of the beam, because it is a moment. So this moment tries to push AC downward like this. So that's why it is deflecting like this. Similarly, this moment tries to push down. You can see the arrowhead. The arrowhead tries to push BC downward. So this beam bends here like this. So this is the deflected shape of the beam. So these are the three quantities you're supposed to find out. That is theta A, theta B, and delta C. So after this, again, because it's a moment, if you want to draw the M or EI diagram, it is obvious that here, this is left side. Uh, now this is going, okay, with respect to C. With respect to C, just check to the left side. So this is clockwise. Clockwise is positive. So this is positive, that is with zero line. This is plus M over EI. The same continues. The same continues up to this portion. And it continues here. Again, with respect to C, right side of C, there is a anti-clockwise. So right side anti-clockwise is positive. So again, this line continues. So it's like a box, rectangular box. So it is M over EI diagram. This is M over bending moment diagram. So next, if you want to find theta A minus theta C. Again, theta A is maximum, theta C is 0 here. So theta A minus theta C is area. Again, that is symmetrical. So if you find only theta A, it is as good as finding theta B with a negative sign. So theta A is theta A minus theta C is equal to area of M over EI diagram between A and C. So between A and C, it's a rectangle. So this is rectangle is length into breadth. So here M over EI is breadth divided by length. Length exactly half the distance, so it is L by 2. So theta is ML over 2EI. Answer is positive clockwise. Theta B is just the opposite, that is minus ML by 2EI. Next, if you want to find deflection, so deflection is maximum deflection, that is theta C. If you want to find theta C, it is the moment of area of M over EI diagram between A and C. M over EI diagram between A and C about point A. Again, it's a support, so you're finding moment about the support. So this is the area which you already found out, this area. ML over 2EI is the area into half of this distance here. Basically up to A and C it is L by 2. Half of L by 2 is L by 4. So this is L by 4. So it is ML square over 8EI. So delta C is ML square over 8EI at the center. This is how we calculate. So remember one thing, for simply support beam, we always calculate maximum slope, maximum deflection, and that's how maximum slope is at the support and maximum deflection is at the center. and we always find the moment with respect to the supports. Okay, that's all with this moment area method. Thank you.